Today's topic is energy distribution in blackbody radiation and Planck's formula for this. Blackbody is such a body which absorbs completely radiations of all possible wavelengths and emits radiations of all possible wavelengths when heated. Lumer and Prinzim studied energy distribution in blackbody radiation at different temperatures. They found that spectrum of blackbody radiation is continuous. That is, at a particular temperature, energy is continuously distributed in different wavelengths. This is shown in this graph where E lambda is plotted against lambda. Lambda is wavelength. E lambda is spectral energy density. Energy density is energy upon volume. Energy density is energy per unit volume. And if we consider a small wavelength range, lambda to lambda plus d lambda is very small. So for wavelength lambda, if we consider this small range lambda to lambda plus d lambda, then we write E lambda d lambda equal to energy density, that is energy upon volume. Then this E lambda is known as spectral energy density. E lambda spectral energy density is equal to energy per unit volume per unit wavelength range. So this is spectral energy density E lambda, energy per unit volume per unit wavelength range, and it is plotted against wavelength lambda. We see that the curve is continuous. Three curves are drawn for three different temperatures. So these curves are continuous. So energy is continuously distributed among different wavelengths lambda. At some wavelength lambda m, value of energy is maximum. Wavelength corresponding to maximum energy, which we write by lambda m, it is displaced towards low wavelength with increasing temperature according to Wien's displacement law, that is lambda m t equal to b, a constant. We see from this graph that E lambda spectral energy density increases with lambda when lambda is small. So when lambda increases, E lambda increases, then it reaches to a maximum value, and then E lambda decreases with increase in lambda. So this value of lambda, which is shown by dotted lines, this value of lambda for which E lambda is maximum, we write this value of lambda as lambda m. M is for maximum. Lambda m means lambda for which E lambda is maximum. And Wien's displacement law is this. Lambda m into t equal to b. B is constant. So this is Wien's displacement law. This shows that when T temperature increases, lambda m will be decreases because lambda m into T is constant. So when T increases, lambda m will be decreases. This is shown by this graph. These are three graphs for three different temperatures. As temperature increases for a particular lambda value of E lambda, spectral energy density increases. So energy or energy density increases for a fixed lambda when temperature T increases. And we show three dotted lines, and the dotted line towards the origin is for large value of temperature, and for this value of lambda m is small. So we see that when the temperature increases, lambda m will be decreases, or it shifts towards low wavelength. This figure shows variation of spectral energy density E lambda, which is radiated energy per unit volume in unit wavelength range. And this is plotted with wavelength lambda at different temperatures. This curve is known as energy distribution curve. Now we see Planck's formula. Classical theory failed to explain about these facts. Classical theory fails to explain this type of energy distribution in blackbody radiation. To explain the energy distribution in blackbody radiation, Planck assumed that radiation emission and absorption of radiation energy in blackbody is not continuous, but it is in the form of small bundles of energy known as quanta or photon. So to explain this energy distribution in blackbody radiation, Planck gives the hypothesis of quanta or photon, and he assumed that energy in blackbody radiation is not continuous. It is absorbed or emitted in the form of small bundles known as quanta or photon. Photon of frequency nu have energy E equal to h nu. This is Planck's formula for energy of photon. If frequency of photon is nu, then its energy E equal to h nu. H is a constant known as Planck's constant. And momentum of photon P is given by P equal to E upon C, and E energy is h nu, so momentum P is h nu upon C. Photons are identical and indistinguishable particles having spin s equal to 1. So these are bosons and obeys Bose-Einstein statistics. According to Bose-Einstein distribution law, we have this formula: Ni equal to Gi upon e to the power alpha plus beta Ei minus 1. This is Bose-Einstein distribution formula. Ni is number of particles and Gi is number of states alpha and beta are constants. These are undetermined multipliers. Alpha, constant alpha is introduced from the condition that total number of particles are constant. But for black body radiation, total radiation energy is constant. Constant alpha is introduced from the condition that total number of particles are constant, and constant beta is introduced from the condition that total energy is constant. But for black body radiation, total radiation energy is constant, but total number of photons may change. So restriction of total number of particles, capital N equal to summation Ni equal to constant, or Dn equal to 0, this condition is not applicable here. So undetermined multiplier alpha is 0. Then substituting alpha equal to 0 in equation 1, we find this distribution law, Bose-Einstein distribution law, as Ni equal to Gi upon e to the power beta Ei minus 1. If in frequency range nu to nu plus d nu, for frequency mu, we consider a small range, nu to nu plus d nu. D nu is a small change in frequency nu. So we consider this frequency range nu to nu plus d nu. Then number of accessible microstates per unit volume for photons is G nu d nu. Then in this frequency range nu to nu plus d nu, number of photons per unit volume is given by n nu d nu equal to G nu d nu upon e to the power h nu upon kt minus 1. Here in equation 2, we write G nu d nu for Gi. Gi is number of states. So we write in place of Gi as G nu d nu. This is also number of states in this frequency range nu to nu plus d nu. And Ni in equation 2 is number of particles, that is number of photons. So for Ni we write n nu d nu, it is the number of photons in this frequency range nu to nu plus d nu. And we consider this for unit volume. And then we write for Ei as h nu in this frequency range nu to nu plus d nu. We can assume frequency almost equal to nu. D nu is very small. Then energy Ei will be equal to h nu, and this constant beta is equal to 1 upon kt. T is absolute temperature and K is Boltzmann constant. So in right hand side, in denominator, this exponential becomes e to the power h nu upon kt. H nu is for Ei, energy, and for beta we write 1 upon kt. So from Bose-Einstein distribution law, we write this equation for number of photons per unit volume in the frequency range nu to nu plus d nu. So to find this number of photons per unit volume in the frequency range nu to nu plus d nu, we have to find G nu d nu, which is number of microstates per unit volume in the frequency range nu 2 nu plus d nu. Now we calculate the number of accessible microstates per unit volume in frequency range nu to nu plus d nu. For this, we calculate the number of accessible microstates for photons per unit volume in momentum range p to p plus dp. So we first consider the number of accessible microstates for photons in this momentum range p to p plus dp. For this, we consider a phase space, which is 6-dimensional space, having 6 axes, 3 for position x, y, z, and 3 for momentum components px, py, pz. So volume element in phase space in this momentum range p to p plus dp will be equal to volume element in position space into volume element in momentum space. Phase space is divided into two parts. One is position space and one is momentum space. Volume element in position space is taken as 1 because we consider unit volume. We want to find the number of microstates in unit volume. So volume element in position space is taken as 1, and for volume element in momentum space in this momentum range p to p plus dp, we draw this diagram. This is for momentum space having 3 axes for 3 components of momentum px, py, pz. We draw a sphere of radius p with origin as its center, and then we draw a sphere of momentum p plus dp. So we draw 2 spheres having same center, one for radius p and other is for radius p plus dp. For the space between these 2 spheres, momentum will be in the range p to p plus dp. So the region which is shown between these 2 spheres, it is the region for which momentum is in the range p to p plus dp. So volume of this momentum space in this momentum range p to p plus dp will be volume of this portion between 2 spheres, and this volume is equal to 4 pi p square dp. 4 pi p square is surface or area of this sphere of radius p, and if we multiply by dp, the distance dp is shown in this diagram. If we multiply by dp, then this will give the volume of this region having this distance dp. So volume of momentum space in momentum range p to p plus dp is determined in this way, and it is equal to 4 pi p square into dp. So momentum volume element in phase space now will becomes equal to 1 into 4 pi p square dp. Now we put the value of momentum. Momentum p of photon is equal to E upon c, and E is h nu. So momentum p equal to h nu upon c, and if we differentiate this, then this will give dp. H and C are constant, so dp is h upon c into d nu. Differentiation of nu is d nu. Put the value of p and dp, then volume element in phase space in momentum range p to p plus dp will become 4 pi h nu upon c square into h d nu upon c. This is 4 pi h cube nu square d nu upon c cube. In phase space, minimum volume of a phase cell is h cube. So, number of accessible microstates per unit volume in this frequency range nu to nu plus d nu is given by dividing this volume by h cube. So, we divide by h cube the above volume. So, this will give the number of microstates in this given frequency range nu to nu plus d nu, and it is equal to 4 pi h cube nu square d nu upon c cube upon h cube. H cube is cancelled out and it will comes out equal to 4 pi nu square upon c cube d nu. There may be two modes of polarization of photon. So, number of accessible microstates per unit volume in this frequency range nu to nu plus d nu will be 2 times. It is doubled because there are two modes for polarization of photon. So, number of accessible microstates per unit volume in the given frequency range nu to nu plus d nu, we write it by g nu d nu, and it is equal to 2 times 4 pi nu square upon c cube d nu, and it is equal to 8 pi nu square upon c cube d nu. Now we put the this value of g nu d nu in this equation for n nu d nu. This is equation 3. Then this will give the value of n nu d nu, number of photons per unit volume in the given frequency range nu to nu plus d nu. So, n nu d nu will be equal to 8 pi nu square upon c cube d nu divided by e to the power h nu upon kt minus 1. These are the number of photons per unit volume in the given frequency range, and frequency range is nu to nu plus d nu. In this frequency range, we assume frequency approximately equal to nu. Then energy of each photon is h nu. So, energy of these n nu d nu photons will be h nu times this number of photons. So, energy per unit volume in the frequency range nu to nu plus d nu, we write this by E nu d nu. E nu d nu is energy in this frequency range nu to nu plus d nu per unit volume. It will be h nu times this n nu d nu. So, it is h nu times 8 pi nu square upon c cube d nu upon e to the power h nu upon kt minus 1, and this will be equal to h e nu d nu will be equal to 8 pi h nu cube upon c cube d nu upon e to the power h nu upon kt minus 1. This equation 6. This is the Planck's formula. E nu d nu is energy density per, it is the energy per unit volume in the frequency range nu to nu plus d nu, and it is equal to 8 pi h nu cube upon c cube d nu upon e to the power h nu upon kt minus 1. This is the Planck's formula in terms of frequency nu. We can find the Planck's formula in terms of wavelength lambda also. This is Planck's energy distribution law in terms of frequency nu. To find Planck's energy distribution law in terms of wavelength lambda, we write nu equal to c upon lambda. This is the relation between frequency nu and wavelength lambda. C is a constant equal to speed of light in vacuum. Since the radiation photons travel with the speed of light, so nu equal to c upon lambda, c equal to nu lambda. So nu equal to c upon lambda and d nu equal to minus c upon lambda square d lambda. C is constant. If we differentiate this, then this will give d nu. Differentiation of 1 upon lambda is minus 1 upon lambda square d lambda. So we put the value of nu equal to c upon lambda, and we put the value of d nu, which is equal to minus c upon lambda square d lambda, in the right hand side of this relation. Then this will give the energy density in terms of wavelength lambda, and then we write E lambda d lambda in place of E nu d nu. So this will give E lambda d lambda. Correct this, it is not E lambda d nu, it is E lambda d lambda. It is also energy density, but it is for wavelength range lambda to lambda plus d lambda. We have put the value of nu equal to c upon lambda and put the value of d nu equal to minus c upon lambda square d lambda. Minus sign is not taken here because energy density is not negative, it is always positive, so minus sign is not taken here. Then E lambda d lambda will be equal to 8 pi hc upon lambda to the power 5 into 1 upon e to the power hc upon lambda kt minus 1 into d lambda. This is Planck's energy distribution law in terms of wavelength lambda. Results obtained by this formula is in agreement with experiments. From this relation, if we find E lambda, then E lambda is equal to 8 pi hc upon lambda to the power 5 1 upon e to the power hc upon lambda kt minus 1. 8 pi hc is constant, so E lambda depend upon these two factors. One is 1 upon lambda to the power 5 and other is 1 upon e to the power hc upon lambda kt minus 1. The factor 1 upon lambda to the power 5, when lambda is increased, this factor 1 upon lambda to the power 5 is decreased. And the other factor, which is 1 upon e to the power hc upon lambda kt minus 1, this factor increases with increase in lambda. So initially, when lambda is small, this factor 1 upon e to the power hc upon lambda kt minus 1, it is effective. So value of E lambda increases with increase in lambda due to this factor 1 upon e to the power hc upon lambda kt minus 1. So E lambda initially, when lambda is small, initially it increases with lambda, then reaches to a maximum value, and then it decreases, and because this second factor 1 upon lambda to the power 5, this becomes effective for large values of lambda, and due to this factor 1 upon lambda to the power 5, E lambda decreases with increase in lambda, which is shown in this energy distribution curve. Initially E lambda increases with increase in lambda when lambda is small. So E lambda increases initially with lambda, reaches to a maximum value, and then it decreases with increase in lambda. So this energy distribution curve can be explained by this Planck's formula E lambda d lambda is equal to 8 pi hc upon lambda to the power 5 1 upon e to the power hc upon lambda kt minus 1 d lambda. Now we derive derivation of Rayleigh Jeans and Wien's formula from Planck's law. This is Planck's law. E lambda d lambda equal to 8 pi hc upon lambda to the power 5 into 1 upon e to the power hc upon lambda kt minus 1 d lambda. From this Planck's law, we find Rayleigh Jeans law and Wien's law. Case first for small wavelengths. When wavelength is small, in this formula, in exponential, we have e to the power hc upon lambda kt. Hc upon lambda is energy. We consider it in numerator. Then in denominator, we have kt, which is also thermal energy. So if lambda is small, then hc upon lambda, this energy is much greater than kt. Lambda is small, then hc upon lambda will be large. It is much greater than kt. Then this term in exponential hc upon lambda kt will be very large. Then we can neglect 1 in comparison of this exponential e to the power hc upon lambda kt. So when lambda is small, hc upon lambda is much greater than kt. This exponential quantity will be very large in comparison to 1. So we neglect 1 here. And then this formula will becomes E lambda d lambda equal to 8 pi hc upon lambda to the power 5 e to the power minus hc upon lambda kt d lambda. This can be written as c1 upon lambda to the power 5 e to the power minus c2 upon lambda t d lambda. 8 pi hc is written as constant c1, and in exponential hc upon k is written as c2. So we find this formula for small wavelengths. E lambda d lambda equal to c1 upon lambda to the power 5 e to the power minus c2 upon lambda t d lambda. This is Wien's formula for small wavelength lambda. Term e to the power minus c2 upon lambda t is more effective, so that value of E lambda increases with increasing lambda. This law explains energy distribution curve in low wavelength region only. Case second is for large wavelengths. When wavelength lambda is large, then hc upon lambda will be much smaller than kt. So hc upon lambda kt is much less than 1. So in this exponential, hc upon lambda kt is much smaller quantity. Then we can expand this exponential by using the formula e to the power x equal to 1 plus x square upon factorial 2 and so on. Square and higher order terms are neglected, and then e to the power hc upon lambda kt minus 1 will becomes equal to 1 plus hc upon lambda kt minus 1. We consider only two terms in this expansion. Square and higher order terms are neglected because hc upon lambda kt is a small quantity. So square, cube and higher order terms are much smaller and neglected. Then in denominator, this e to the power hc upon, it is not e to the power minus, it is e to the power hc upon lambda kt minus 1, and it is equal to 1 plus hc upon lambda kt and minus 1. Plus 1 and minus 1 is cancelled out, and it will becomes equal to hc upon lambda kt. So in this Planck's formula, this term e to the power hc upon lambda kt minus 1 now will become equal to only hc upon lambda kt for large values of lambda. Then E lambda d lambda will becomes 8 pi hc upon lambda to the power 5, 1 upon hc upon lambda kt d lambda, and it is equal to E lambda d lambda equal to 8 pi kt upon lambda to the power 4 d lambda. This is Rayleigh-Jean's formula, which explains energy distribution curve in large wavelength region when wavelength lambda is large, and in this case value of E lambda decreases with increasing lambda because of this factor 1 upon lambda to the power 4. When lambda increases, E lambda decreases. So this is Rayleigh-Jean's law. This explains energy distribution curve for large wavelength region when lambda is large.